So today we're very happy to have Marina Cortes as our second speaker. Marina undertook a PhD at the University of Sussex under the supervision of Andrew Little, who is also visiting, but not in the room. He's upstairs. And then Marina undertook a postdoc at Berkeley, and now she's a Marie Curie Fellow at the University of Edinburgh. And she's also a long-term visitor at the perimeter, and so she kind of agreed to stop by to tell us about lopsided universe.
Thanks so much, Takeshi. It's a big pleasure to be at CITA, finally. I work at Perimeter, and I visit Perimeter quite often. But I always wanted to visit CITA. So thank you, Takeshi, for hosting me, and also Richard Shaw for organizing the seminar. I'm going to talk about some work done with Andrew Little. It's a work that we've done about a year ago on explaining the anomaly of hemispherical anomaly that we see in the CMB. It's a nice exercise as to how you could explain from first principles, how could that hemispherical anomaly come about in the anisotropies that we see in the sky. And so let's get started. I always like to start, particularly this talk, because it was motivated, this work was motivated, of course, by the Planck results coming out. And if we put our 3 generations of CMB experiments together, this is only 20 years worth of data. And so as cosmologists, I find it really positive and optimistic that, 20 years ago we were measuring the CMB anisotropies to 7 degrees. Of course, 10 years ago we would see about 0.3 degrees with WMAP, and Planck, of course, is this exquisite precision that we all love and await more results. So I think for the community, independently of what else may be going on, it is a very positive result, particularly when you put it, of course, everybody knows this picture, but it's still in 20 years to go from there to this precision. It's quite a big achievement. So I'm going to talk about, of course, why the CMB sky looks a little bit like this if you take away the anisotropies. Basically, it's the perturbations are stronger on one hemisphere than the other, and this is in contradiction to the anisotropy of the perturbations generated by inflation. This is galactic coordinates. I suppose it is. The orientation of the hemispherical asymmetries, it's more or less like this. I mean, this is just a pictorial. It's, of course, it's not the measured asymmetry. So the plan is more or less talking about the observations, talking about how he has been explained from a theory point of view, how we can model the asymmetry on the perturbations that we see in the sky. This is what I will tell you. How can we explain why the spectrum looks asymmetric like this from a theoretical point of view? Then you will have, I'll try to explain, argue, how do we calculate the spectrum for this type of models, and then how we obtain the anomaly. So this is a picture that was created at the time. It was actually for our paper by APS. And when the Planck results came out, of course, we were all a bit surprised, positively or negatively, by learning that the anomalies of the CMB, and in particular this difference in the 2 hemispheres, were still present in the Planck data, even if it was the precision was much greater compared to WMAP. The uncertainty was also roughly the same that WMAP had, and not only that, we learned that it extended to much lower multipoles, so it was not just an artifact of very large scales, which could have easily been a statistical fluke at WMAP accuracies, but Planck saw exactly the same thing, and so a lot of theorists started to look at a little bit even more seriously, because it had been corroborated by another experiment, another instrument other than WMAP. So this is how we normally model the hemispherical symmetry. Here you have our usual isotropic spectrum of perturbations that generates large-scale structure. Here we have these P's, the orientation of maximum asymmetry in the sky, and the A is the amplitude of that asymmetry. So to get the full spectrum of perturbations, including the asymmetry, you just have the spectrum given by the usual isotropic spectrum plus an orientation, a vector in the sky, which is multiplied by the usual isotropic spectrum. This essentially means that the density, what we're observing, the implications of what we're observing for our modeling, for our theory building, it means that the density of matter and radiations is oscillating more strongly on one part of the hemisphere than the other. And of course, before we jump onto model building and explaining these, we need to be careful that the statistical significance, it's about 3 sigma of this particular hemispherical difference. And so it's still a debate, and as we know, and a lot of people here know very well because they work on the CMB, the CMB, it's a field for performing the large number of tests that you can perform, and you can find a lot of information on the CMB. So we are bound, because we perform so many tests for any sort of features, we are bound to find something which is just statistically possible, but not significant, cannot be a real feature of the underlying model. So here we now know that it persists to much smaller scale. We need, if we believe that it is a real feature, we need a phenomenological, it's like a dipole modulation of our model to explain these perturbations and why they vary differently. And this is a quote that I've learned, I saw once going to a statistician's conference, which they are always often they're a little bit careful or even cynical about features that we may find in our theories, because you can massage data for as long as you like, and you will eventually find some oddities that are not predicted by the theory. So if it's a statistical fluke, there's absolutely nothing that we will ever learn more from it, because we just have one realization of the sky, and it could be just a random Gaussian fluctuation within the possible realizations that we can have. However, if it is a real feature resulting from the underlying theory of generation of structure, it is quite relevant, because these are scales which are outside the horizon now. If you imagine the wavelengths of the perturbation that is generating this asymmetry, it's not inside, it's the size of the horizon maximum, and quite possible outside the horizon. So if it's physics that happened before the inflation scales that we see today, and so it's quite positive in that sense. If this is coming from a physical model. Now, if we are model builders, this is challenging, because in order to explain these, we need to make perturbations stronger on one side as opposed to the other, but the mean temperature is constant across the sky. It's just the spectrum of perturbations that is varying. It needs to, whatever model we make, needs to maintain mean temperature constant to 0.1%, and the Gaussianity, of course, is also very well constrained by Planck. So here we have 1 in 10,000 at any angular scale. So let's try to look at what we could do to add this new feature onto the CMB sky coming from an inflationary origin, perhaps, because we all love the perturbations generated by inflation, and of course we would like to keep it as an origin of perturbations. And so the idea that was created or came up with in 2008 by Eric Czech, Sean Carroll, and Mark Kamionkowski was that this is our Hubble horizon today. Here are the scales, the perturbation scales coming from inflation, so smaller scales entering the horizon today. And this is the size of a long wavelength perturbation that would be superposed on top of our usual CMB skies. So it is very large scale, and it is super horizon. And that's why when this gets added onto the usual inflationary perturbations, it would create a symmetry in two hemispheres. I'm going to go a little bit over how inflation generates perturbations, just because I'm not sure if everybody here know. A lot of you work on inflation. So inflation is just our mechanism for giving acceleration and solving the cosmological problems of flatness and the perturbations in the early universe. We usually, this is the most pictorial, simplest model of what inflation does that you can create. Here you have the scalar field phi, which is some scalar field and giving a potential in the y-axis. What we need from inflation is that it's got a flat portion of its potential, and the field phi starts more or less out here, and it's rolling down that potential. The perturbations are generated while the field is around here. At some point, inflation needs to end, so this potential then needs to change sharply. It needs to start rolling, stopping the rolling and start oscillating here around the minimum. This is the time when the scalar field decays and generates the thermal bath, or we get our radiation bath back. So usually the only parameters, or the most important parameters that we need, is that the potential needs to be very close to flatness. So the first derivative of the potential needs to be small. It needs to stay small for long enough because we want it to give enough expansion to solve all our cosmological problems. So the second derivative of the potential also needs to be small, and usually we associate these two parameters of the flatness and curvature of the potential when the perturbations are being generated to these scalar spectral index that we then measure with Planck and WMAP. And has these, so by measuring the spectrum of the perturbations on the CMB sky, we learned about the flatness and the curvature of the infotron potential. And so this is in the picture that I was drawing before. This is just the perturbations, our usual spectrum of perturbations generated at the horizon. And then this is just the amplitude of perturbations, which gives us the energy density of the potential. So inflation source is the continuum. This is where we all know. And so what can create these long wavelengths? We know from work before, we know that if we add something like this wave mode, onto the continuum of perturbations, you explain the CMB sky. You explain how Planck is observing that asymmetry. But we don't know, there was no explanation to what could be the source of this wave mode. And because Planck has measured it to be it has confirmed the double map predictions, we really wanted to explain or give a phenomenological explanation for what this could be. And so what Andrew and I came up with is what if this was a scale that indicates a departure from flatness in the universe? So we know that our universe is very close to flatness, but if this indicated some scale of curvature, then this would the spectrum would look like this. And in particular, if you have negative curvature, which gives a sort of a saddle geometry in hyperbolic geometry, you would effectively see one side of the hemisphere more perturbed than the other. Exactly like what we want to have here. So will be an explanation for this. Now, we know that Planck has measured flatness to the percent level. And we know that any departure from 1 is going to constrain the maximum radius of curvature. So the constraints on omega measure the flatness, the radius of curvature is 10 times the Hubble radius. But if you then compute the observable universe, flatness is only measured to 3 times the size of our horizon. So it's not an exceedingly large number as we would expect when we know that Planck's measured the curvature to be so small. We could have a radius of curvature which is 3 times the size of our universe today. So the constraints on curvature are strong, but it's still not many times the horizon.
So Marina, you mentioned about the negative curvature. Mm-hmm. Does it have to be negative, or can it be positive?
The positive doesn't give you the hyperbolic geometry, the saddle geometry that effectively looks as if one part is over density and one part is under density. I think that's only, I don't know how to compute the spectrum because as you know, it was very difficult to compute the power spectrum for open geometries. And trivially, I don't know how it would look if the curvature was positive. But I don't think it would have these plus and minus.
I guess here you have the open inflection line, so that's why.
Yes, yeah, exactly. So that's.
So would this seem to be different than the usual notion of an open FRW in the sense that you need to be anisotropic? Or can this be isotropic negative curvature and still get
yes.
an anisotropic signature?
Yes, yeah. So the mechanism that's going to produce the curvature is going to be produced before the inflation perturbations are generated. I'm just going to explain that right now. So you'll produce the open geometry, and then the universe will still inflate to give.
Isotropic open geometry still?
It's isotropic open geometry, yes, yeah. It's just that effectively the hyperbolic geometry, the open geometry, looks as if one side of the universe is as hotter than the other or more perturbed. But the small scale anisotropies are still there as we're going to create it. There's a difference. When I say isotropic here, I will mean that all the inflation anisotropies, which are really small scales, and these anisotropies, of course, 2 hemispheres. so which is a much larger difference in isotropy than we are usually used to when we talk about the inflation small scale anisotropies. Okay, so this is just how you create that negative curvature. And models that create open universe, so models that have create a negative curvature, were proposed very early on in the 1990s. Were very studied ever since then, and it basically just you create it again by having a scalar field phi here and a scalar field potential, and this is a tunneling potential. The field starts its position here in a false vacuum, and because we are in a quantum regime, the field starts quantum tunneling here to the true vacuum and creates, this is a bubble, creates a bubble of true vacuum or close to the true vacuum. And we call these are phase transitions, so the field starts here in the false vacuum, tunnels to the true vacuum, and it tunnels through a first order phase transition because the transition is not continuous, discontinuous. And you may have heard of phase transitions that are second order and they are continuous in field space. And this is, for example, the Mexican hat that you will have for sure have heard associated to the Higgs boson, for example. So this is just to compare. And so the open universe model says that our universe is a bubble that nucleated from a false vacuum, and we always see is a bubble, but we are inside a meta-universe which is much larger and has a higher false vacuum energy. And so the way that you can see these is if we are in a bubble, and outside, you have a region of higher energy density. It looks as if you yourself are in an underdense region, and so the geometry is going to look like it's an open geometry, and the curvature will appear to be negative. So this is what I said. Bubble nucleation is the process that happens here. And I don't know if you've heard of the Coleman-de Lucia instanton, but it's usually associated to these. And over at PI, Neil Turok is now doing a very interesting work, just as a side, on showing if the Coleman-de Lucian bubble nucleation is valid. It can be a physical mechanism or not. Okay, said this. And so what does that mean if we are in an open universe, but if it's a negative curvature, the volume is infinite, but we are enclosed within a finite bubble? And so it just means that the universe for us is just, we nucleate here, we create a bubble. The bubble starts expanding, and at each time instant, our universe is just an hypersurface of constant time, and which is enclosed within the larger bubble, and the whole region is the meta-universe. But our whole universe is infinite inside the bubble. And so what does it have to do with the asymmetry? When the universe tunnels and creates a bubble, that bubble will have, because we are again in the quantum regime, the bubble will acquire a fluctuation just as the scalar field does when it's inflating. But this is a discontinuous transition. So the fluctuation gets imprinted on the mode of the size of the horizon that is leaving the horizon at that time. As you know, the perturbations in inflation are generated when the mode, the universe is expanding and the mode of the perturbation leaves the horizon. So what we then needed to find out was how does that quantum fluctuation gets calculated on the bubble. How does it get imprinted on the bubble when the bubble is created, and how does that look when you then have your usual inflation perturbations? So this is just a pictorial graph, and the spectrum does not look like this, but I chosen to show it like this because it helps a lot. We all know this is the potential in a hydrogen atom, and the levels of the states, energy states in a hydrogen atom, and we know that the bound states are kind of discrete, and then when the electron becomes free, it's a continuum of states. And so this is more or less what happens in the model, where you have one horizon wavelength mode, which then is superposed on the continuum of perturbations that inflation generates. And so when the bubble is created, the mode that is leaving the horizon at that time is a one mode with a distinct size of all the other inflationary generated perturbations. And this is all that, this is to give an example of something else that looks like this. It's the hydrogen atom, but it's, of course, this is just an analogy. And we will call this, of course, is the supercurvature mode that gets generated when the bubble leaves the horizon. So this, I already explained this, when we decompose the modes in a Fourier decomposition, there is, because we are not in flat geometry, the wavelengths that are larger than the curvature scale are going to be modified like that. And so this is, then when we look at the CMB sky, this is the analogy. The inflation perturbations are generated usually, so they give this spectrum, and the single mode, the supercurvature mode, will give like a sort of a dipole modulation there. And then it's of course not exactly this is how it happens, but you can imagine that you are superposing the supercurvature mode onto the inflation sky.
I don't know much about open inflation, but when you get the single, when you get the supercurvature mode, don't you get like a curvature mode of twice the wavelength or 3 times? Like, don't you get like
You get defined, the wave mode is well defined. I'll give you, later on I'll give you. It's defined in terms of the curvature of the Faust vacuum and the amplitude, the energy of the Faust vacuum. And that helps too. It's not just any mode, it's 3. The wave number is very well determined. I don't know. I'll show you how what is done. So this is the work. This was computed by Misao Sasaki and collaborators in 1996, who that computed what happens when you try to create, when you compute the power spectrum generated in a bubble nucleation, if you want inflation to be a quantum tunneling. So this is, we're not going to discuss this very much. The modes that are under curvature, so smaller than the curvature radius, just generate the continuums. These are the wave numbers. And then this is also just for showing there is one supercurvature mode which has p smaller than 0. And these described fluctuations in scales larger than our horizon. And so what this will represent is that the amplitude of the fluctuation mode is going to be given by the ratio of the false vacuum energy density over the true vacuum energy density. This, of course, it's not going to be equally 0. So basically what they computed is that the amplitude of the super curvature mode was going to be proportional to the ratio of these two vacuum densities. And then, so you have here the usual power spectrum, which is this one, and then the power spectrum of the single long curvature mode is going to be proportional to the usual power spectrum. So we have everything, and now we want to build the model. We need a tunneling area, which was like what I showed before, and then after that long curvature mode is formed, we still need inflation to happen and give us all our spectrum of fluctuations. So it's a tunneling area followed by an almost flat area where our usual cosmology is regained and the field is rolling. And this was found to be, or if inflation is already usually fine-tuned, we have a lot of problems with choosing the parameters by hand, that they are not naturally appearing in the theory. If we say something, oh, now I need a tunneling potential, and then I need a fine-tuned one, it's almost like building the model piece by piece. So a lot of people had a lot of problems with this, and I'm sympathetic. So people think it's better to have one field that is tunneling, and we call that psi, and then we have the second field, so another direction, orthogonal direction appears, and that direction will give you inflation. And that can be said to be more natural within a landscape of possible scalar fields. So the one field has the false vacuum and tunnels. The inflaton gets the long wavelength mode as it bubbles, tunnels into the true vacuum, and then in the plateau, it produces the continuum spectrum of perturbations. And we would think that we are done, but there's something very simple to realize, which is if we have one field giving all the quantum fluctuations, and then that field all of a sudden has a dipole, a hemispherical perturbation which is very large. Of course, then immediately the next perturbation in our spherical harmonics is the quadrupole. And if that field has a large dipole, it's going to have a large quadrupole. And we have very stringent constraints on the quadrupole. So what turns out to be is that you cannot have the same field generating the hemispherical symmetry and your usual continuum spectrum of inflation perturbations. So it turns out that we need one more field. And so one gives the supercurvature mode, one field gives the anisotropies, and so in total you will have 3. The third gives the tunneling. And there is a simple mechanism to generate these. And I'm not sure, since Takeshi works here and is such an expert on curvaton, I will assume everyone knows already the curvaton model very well. But I will explain it a little bit as well. So what happens is that you've got a bubble mode which is formed during tunneling. It leaves the horizon, so it's outside the horizon. And then inflation takes place and generates the continuum spectrum. And so but we need that mode that is now very, very much outside the horizon to come back at some point and give the asymmetry, the hemispherical asymmetry. So this is exactly what this field, the curvaton field does, which is another scalar field. What it can do if you use it, the second scalar field gets the tunneling mode, leaves the horizon. The spectrum of inflation is generated. The inflaton gives radiation, as usual. And then, much later, the curvaton comes back inside the horizon and imprints that asymmetry, the long curvature mode, onto what we already have inside the horizon. And so basically, this will be given by the curvaton and this by the inflaton. And I'm just going to skip very fast over this. But this is basically what happens with two scalar fields. Over here, it's the scale factor in logarithm. And here is the energy density. And you have here two fields, the energy density of the inflaton and the energy density of the curvaton. So the energy density of the curvaton is much higher, and it's giving inflation. It's constant, so it's giving acceleration. And the curvaton is over here. It's got much less energy density, and it's also constant. And this is also getting quantum fluctuations. Then the curvaton here, the inflaton decays and starts to behave like radiation. So it starts to the energy density redshifts away. And at some point, the curvaton also later on decays, starts to oscillate around the minimum of the potential and overtakes the density of the radiation here. And when it becomes dominant, it gives its perturbations onto the radiation that we already have inside the horizon. And then you just resume your cosmology there. So what's useful about the curvaton, other than for these, is that if you have a model coming from fundamental or particle physics that has some funny shape of the potential that will give you give you observations that are not what we see in the CMB. So if it will give you a red tilt or a blue tilted, you can have still that field giving the accelerated expansion, and then you use this to give you the spectral tilt and the observations that you need. It's a fiddle with the scalar fields, but it's very useful, and it's been studied for several years proposed by those people there, and I just have a work with Andrew as well on that. Yes?
I mean, construct model where inflation can decay into curvature.
Oh, the inflaton can decay. If that's possible? Are you asking if that's possible?
Yeah.
I think that's possible. The problem with that, so they would decay around here. This is instant reheating model. The problem with that is that we don't want the quantum fluctuations of this guy. If we have the curvaton, it means that this guy is doing something funny that we don't see in the sky, so we want to get rid of it. And so if it decays, it will have those funny-looking spectrum of perturbations that we as model builders usually wouldn't want. So it's like a disguise. The curvaton sort of puts away the mess that the inflaton makes when you don't want it. Okay, so let's come back to the asymmetry. Now it's very simple. We have now our parameters of the tunneling potential. So we have the energy density of the vacuum, the curvature of the vacuum, so the mass of the tunneling field here. We have the energy density of the true vacuum. This is what you are asking about. The wave number of the mode that is creating during nucleation is related to the parameters of the false vacuum by this ratio. And now we're going to use these parameters of our model to connect to the A, which is what Planck has measured. And we're going to make our model to suit the Planck observations. Another number that we're going to use is, of course, the non-Gaussianity is now very well measured by Planck to be very small. And you can easily imagine that if I have a Gaussian sky and I mix it with something larger, which has a large amplitude like that, it's going to become non-Gaussian very easily. So that's another number that's going to be constraining what we can do with the model. So basically, this now are just building the model. So this is the amplitude of the asymmetry, your non-Gaussianity, the wave number, the amplitudes of the perturbations, and our curvature. And David Leith last year has created a way to measure, constrain all these parameters that we put in the model to give the asymmetry. The x here is the distance to the large-scale, last scattering surface, and the power spectrum of the supercurvature mode is just going to be like a delta function, which just has that wave number.
But I mean, that k is involved into many L's, so how does that projection take into account?
The k.
Or is it not taken into account?
Yes, it is, exactly. So when you calculate the influence of one supercurvature mode onto the usual continuum spectrum, the influence is over a large range.
But then on the CMB, it's involved with the transfer function of radiation transfer function.
Yes.
Mixes up the k, and then there's also the other.
Yeah.
So this is a k which is imprinted on the sphere.
This is
the distance, right?
Yes. This is you can imagine if the k of maximum asymmetry. So that modeling that they have, that Planck's put out, this it's the direction of maximum asymmetry. Of course, there's asymmetry everywhere, but so that if you wanted, there's a wave number that which has the maximum effect. But then, of course, when you measure on the CLs, it's going to have it's not going to just affect the composition. Okay, so. So we have the FNL, non-Gaussianity. Like I said, the quadrupole needs to be very small. You can't blow up the dipole without blowing up the quadrupole. And then you just put all these ingredients together and start measuring. We have constraints on FNL. We've got constraints on curvature. And we saturate the quadrupole. And essentially, give something like this. So you either have, if you want to have an asymmetry, you either have to blow up non-Gaussianity or create curvature. And so you can't just get any power of the symmetry that we want. And remember that this is 0.07 measured by Planck. This is maximum 10-ish. So if this is 10-ish, you still get the asymmetry that you want, but if this is larger, you don't get it anymore. And then, so if this is around 10, you can have it. You can have the asymmetry if the curvature is given by that number. And this is just. It's not as simple as I'm picturing you. So this is work in progress with Andrew and Takeshi, which is in reality. Planck has measured these over multiples essentially smaller than 60, but there is more work done. So last year, Flender and Hotchkiss have measured the asymmetry at much larger multiples, and notice the difference. It's constrained to be very, very small at 10 megaparsecs. And a few years ago, Chris Hirata also got from stripe 82, we got a measure of the quasar number counts of quasars. It's also giving an A very, very small. So clearly this A needs to be K dependent. You can't just have an asymmetry which is visible at all scales. And that's exactly what we're trying to create, a scale-dependent FNL model, which is coming from the curvaton and still fit all those. So FNL needs to be satisfying these. It needs to be very small here and very small here. So that's what we're doing right now. And to finish, I'll just mention the cool implication of this, of us finding out what happened before inflation. And if you ever heard anything about inflation, was that it erases all that's happened before. It's either redshifted or stretched or diluted. You don't have, the inflation erases everything that happened before. With this case, you retain a curvature scale, and like I said, you will learn a little bit about the pre-inflationary epoch. So maybe you have heard about the work of Leonard Susskind or Raphael Busso from Berkeley and Stanford, where they try to put a measure on this type of inflation called eternal inflation. They tried to find out which vacuum did we come from, what happened, what is the probability that we came from a given vacuum. So, and usually that's not an observable, but in this case it is, because we have the ratio of the two energy densities given by constraint connected to the asymmetry. So this would be our parent vacuum. This would be some vacuum that we are where we are today. And we also, connecting to the asymmetry, can put a constraint on the mass of the field or the curvature of this vacuum here. So we could, in this scenario, we'll try to explain the values of our fundamental theory, the parameters of our fundamental theories that try to explain it coming from eternal inflation. We could have some idea of what type of inflation happened before and where we are coming from. So that's all I have for you today. This is a model that explains that hemispherical asymmetry from first principles, so from a nucleation potential. We have a lopsided universe. The curvaton gives us that lopsided universe. The open inflation can create that lopsidedness. And the universe is still consistent with the curvature, the flatness constraints, and the Gaussianity as well. Oh, and this is, for some reason, we got a ridiculous amount of press for this work, which I think was mainly just because it's a measurement of an open geometry, and for some reason, the press found it very interesting. That's not the main thing. Thank you very much.
So, is there any questions?
Yes.
So I'm still completely confused by the geometric setup of this. So you've got this anomalous mode that's imprinted on a bubble, right? So a sphere around you. And so this mode is actually a 2D mode on that sphere. And then you translate that into a 3D mode, and then that gets transferred onto the CMB, which is not 2D.
Which is another, yeah.
So it's kind of strange because that mode, the 3D mode, is not all affected by that bubble because it's like just this
projection.
transverse one.
Yes, yeah. So it's a bit, if you try to imagine, we've got a bubble, but our universe does not, we are still infinite sheets, a hypersurface within the bubble. And what we see effectively is an underdensity. So it's not so much the wall. When you're computing, it gets imprinted on a wall, but the entire interior of the wall fills that underdensity. So it's more a 3D effect. We don't look...
I understand, but I'm thinking more in the case of when you actually look at the CMB, you are somewhat sensitive to
Only.
parallel versus perpendicular,
Uh-huh.
of where the power's gone. So, and in particular, like if you're looking at total intensity versus polarization, you're sensitive to that projection in different ways. So, well, I mean, maybe you thought about this, but is the signal enhanced in the polarization? Should we expect to see this even more?
To be more
Because the
from.
polarization is more sensitive, it's more peaked when it projects that mode. So if it's projecting that.
Yeah, I understand what you mean.
So what should I expect
The polarization. From what I understand, it's not trivial because this is work that computing the power spectrum in an open geometry is not trivial at all. Those horrendous formulas that the Japanese created in the 90s. But from what I know, Planck right now, the measurement of the asymmetry is limited by the simulations and not. So they don't expect to measure the asymmetry better. It's just the number of simulations are being increased so that you get the statistical uncertainty to higher precision. So from that, I agree that it could have an effect on the polarization maps, but that's not what I hear when I discuss with them. And so it could be that it may improve a bit, but I don't think they're very hopeful that that's what it's going to happen.
On that, show the ignorance of me coming in rather late. So I'm going to ask, first of all, are you making use of the super horizon mode?
Yes.
Super horizon modes are super horizon.
Yes.
So their impact on polarization should actually be quite limited. So that's not what you were talking about, Carl.
Well, I'm just thinking of what's there at recombination. So if it's picking up a mode. So you're saying, because it doesn't track all
It's
back.
actually picking up quite large scale structure. I mean, it's not.
Yeah.
It's not so much a focused thing that involves less scattering surface. It's the whole phenomenology of the open model because it's probing a very large case.
Yes.
And there's always been a controversy of how important these modes are. I somehow recognize that we've come down on the side of them being fundamentally important by the nature of it. So what makes you think they're fundamentally important?
Oh, it's just
How are they generated?
by quantum tunneling.
Are they? I mean, how do you know that?
Oh, I have no idea. I just invented it. I mean,
So you know very well that if the energies are, if the barrier is large, then what the goal is to create a very taut surface without a lot of fluctuations.
very taut.
Well, she's got a double thing, like she's got the
No, but that's okay.
That's a little bit, then you still go to inflation after.
Oh yeah. This is not first order inflation.
I understand that. It's just that when you tunnel through, if that barrier is high, then what it's trying to do is to create a very taut, open universe without large fluctuations that come with memory, right? I mean, it's only when you lower that potential barrier that you start to get fluctuations through the tunneling process being important.
Oh, that's an interesting question, and I know that the height of the barrier impacts the tunneling rate in usual first-order inflation models. Here, we just there's only one mode, so the tunneling rate is not important.
As associated, I mean, mode except for the overall homogeneous thing that you're popping in as a gradient squared cost. And so it's that gradient squared that the tunneling process is trying to minimize. And so what you would be saying is that somehow there is one mode that's actually being singled out as being allowed to be created without a huge grad squared cost. But the grad squared cost is the key thing to bear in mind here.
And so you mean that that gradient is created by this height?
No, the gradient is created by the thing that you're generating that you say is a memory of the tunnel.
Okay, and so what is, all the fluctuations that we see today are created here, and we keep one mode.
Yeah, I know you're keeping one mode, and the question
And
is, I don't actually see justification, even though you have my sympathies, because it's really fun to play with that thing.
Okay, so I'll,
and the question is, under what circumstances you can actually make it work.
okay.
I don't mean for you to go back to the beginning.
Oh, no. It's just that I was not the one that studied that. This was studied by this group, and they have exactly created the spectrum and explained why do you create just the one mode gets excited.
That probably wasn't in a tunnel.
It was in the tunnel, open inflation.
Yeah, it was just an open inflation.
Oh, it's during open inflation that it creates, yeah. Because then they say that the amplitude of the one mode gets enhanced by the ratio of the two vacua. So this is actually a very, very long paper, and it took me a long time to understand it minimally, but that's the justification. We just went and used the result. We certainly didn't compute the power spectrum for open universes.
And did you provide sort of the intuition of what it is actually physically that's being done?
The mode that gets imprinted on the bubble wall leaves the horizon when the field nucleates or tunnels, and then it leaves the horizon, is outside the horizon all the time, and then only comes back after inflation and imprints the modulation after inflation.
So here is the wavelength of the supercurvature mode, something like the size of the bubble. When they say that the universe becomes inhomogeneous at scales corresponding to the nucleated bubble, or
it's not. It can be. It's larger than the bubble, but it's that wavelength creates the radius of curvature, and so from flatness, we put constraints on that size. So the model doesn't predict exactly which one it is, and we know that it cannot be very small because we know the radius of curvature is very large.
so we can continue our discussions of the different stars, and we're going to test Marina and also Andrew after dinner tonight. So if you want to join, please let me know, because I'll be going to make a reservation. So let's thank the speaker again.